Hi, thank you.
Hi, welcome to the November SJAA Imaging SIG meeting. And today we have Ruben Kier, who's AKA the Star Doctor, who's going to tell us all about choosing and framing targets for astrophotography. So please, Ruben, take it away.
Well, thank you very much. Hi. Thank you guys for inviting me. I'm very excited to share my experience. Um, and when I started doing astrophotography, um, back in the early days, about 15 years ago, uh, it was, one of the challenges I had was trying to find what do I want to shoot tonight? What's the best target? And so I'm going to talk about how do we find the best targets? How do we obtain these images with reference to the images that are appropriate for your site, your camera, your seeing, and the altitude of the object within the sky. And then I'll speak a little bit about framing and composition, rule of thirds, and a squint test. So assume that you're just beginning or are considering astrophotography. What do you photograph tonight? So what's the best for the equipment that you have and your location? And what list can you use in order to choose your target? Like many of you, I first started with Messier's catalog, and we all have different books outlining those objects. But we have to remember that those objects were created in the 1700s, long before any astrophotography. There were objects that were felt by Charles Messier to be possibly confused with comets. And he was using this as a guide to other comet hunters. He was trying to gain access to the Academy of Sciences, and he was hoping to do that by discovering a bunch of comets, for which he was not very successful. But he kept the list of things that really were known to a lot of comet hunters back then, but he cataloged them, and these were a list of potential mistakes. So these were just a bunch of faint fuzzies, not necessarily the brightest or the most beautiful through the eyepiece, but ones that he felt could be confused with comets. Subsequent to that, in 1995, Patrick Moore, his middle name, I think mother's family name was Caldwell, came up with another list of 109 objects that he felt were interesting. He was either editor or on the editorial board of Sky and Telescope magazine, and he collected this list, and he thought that these ones would be interesting for visual observers. But it also included some small and challenging objects, not just the brightest ones. And half of those are really too low in the sky for northern observers. Maybe you guys in San Diego could reach a few more than I could. My latitude is 42. Yours is probably closer to 30. But still, there are a lot of them really are quite low objects. Another list that we've all referred to is the Herschel 400. This Herschel 400 was not a list by Herschel. He actually had a catalog of 2,477 objects. Many of them were extremely faint, and again, objects that he didn't know what they were. He just, noticed that they were fuzzy objects. Some had spiral shapes. Some, were clustered, but clusters of stars. But this list, a subset of this list, was compiled by the St. Augustine Ancient Astronomy Club, and they compiled 400 objects that they felt would challenge observers with larger telescopes. And the Astronomical League adopted it, so many of you have actually may have already gotten your Herschel 400 objects. But again, these are not for photography. These are visual objects. Steve O'Meara. Now, if you've ever seen Steve O'Meara, he's got these eyes that are just huge. And I think that, he can see, I think his limiting magnitude, he can see down to 8th magnitude, I think. And he found another 109 objects that he called hidden treasures to fill in the gaps. And some of them are very nice for astrophotography, but he wasn't doing astrophotography. He was, again, doing visual. And he was also observing from Hawaii, which I think is latitude of about 10. So this was had a lot of objects that were down in the southern hemisphere. or at least, not really visible from where we are in the Northern Hemisphere. So these are the limitations of visual catalogs, which I think you probably know. These are visual, not photographic value. Open clusters we know are much nicer visually than they are photographically. They can be, uh, they can really pop to your telescope, to your eye, but not necessarily to the camera. Globular clusters are interesting, but they don't have a lot of variety. Elliptical galaxies may be bright, but they have no variety. They're just a fuzzy blob, even at higher magnification. And planetary nebula are interesting, but most of them are are really too small to show detail in an amateur image. And from these other catalogs, many are too low for northern observers. The other thing that was difficult is these were not organized by the calendar. So now how do you know which one to photograph tonight? The most important thing when you choose a target to image is make sure that it's something that you really want to see, really want to gather the detail of. Think ahead of time what the composition you want to make, because if it doesn't inspire you, you don't want to spend, 4, 6, 8 hours of photographing it, and then at least an equal number of time processing it. Because if it's not going to impress you, it's certainly not going to impress your friends and family that you're trying to wow them with your, prowess. You want to make sure it's bright enough to image with your sight. And what I try to do is for an average backyard observer with an average camera to at least be able to get a decent image in 2 hours. At least that's what I try to do when I put together my list. You want it to be large enough to show detail, which in most imaging systems has to be at least 5 arc minutes. And for northern observers, you want a declination above minus 25 degrees for the US mainland, because higher is easier when starting out. And objects below that level are difficult to image. And so where can you image these objects? Well, I happen to live in the highest light polluted area in the world, or one of them. This is where I am, where this blue star is. And so this image was taken probably 15 years ago. So of course, light pollution is worse. So I found a place that's about as dark as I could get where this star is, kind of halfway between Albany and Hartford, Connecticut, where I could find magnitude 6 skies, yet still be only an hour and a half from my home. I started imaging from my backyard in a light polluted suburb. So even without narrowband imaging, a third of the pictures that were in my book were actually from the light polluted backyard, and you can actually do well with star clusters and with planetary nebula from a somewhat light polluted sky, because it all depends on the brightness of your object compared to your background and how you could suppress light pollution gradients. But of course, I'm now imaging from my observatory, which is much better skies. So as I mentioned, open clusters, although they aren't necessarily the most interesting object if you're photographing from light polluted area, it's easy with various programs to remove light pollution gradients compared to, say, a nebula that's extremely difficult. Bright condensed objects such as globular clusters and bright galaxies and planetary nebula are still within your realm from light polluted areas. And then I'm going to mention a little bit about light suppression filters. And I don't see as many of them anymore because now a lot of people are doing narrowband. But if you still want to do broadband, one of the things that you can do is you can put on one of these light pollution filters that fit. Lumicron makes them. They suppress light pollution from mercury vapor lights. Of course, now that we're moving to more and more LED lights, especially the street lights and commercial lighting, those filters probably are not going to be as effective anymore. But you can also, try that filter in place of your luminance or clear filter if you have a filter wheel and are doing LRGB imaging. You can also just, if you're doing LRGB imaging, just don't do the luminance, just do RGB. And that'll help with the light pollution. It'll help you get rid of gradients. If you do, you can do narrowband. And at the time that I was uh, publishing my book, the only hydrogen alpha, the only narrowband filters were hydrogen alpha. But what I found is that if I was going to be doing just hydrogen alpha imaging as the primary imaging source, not as the just to add an extra luminance layer. If I was using hydrogen alpha basically as a luminance, I would use a wider band hydrogen alpha filter in order to get some of the natural balances of grayscale in a nebula and not just be confined to the hydrogen alpha wavelength. I mentioned that planetary nebula are a reasonable target for urban imagers. You can do RGB imaging of a planetary nebula and still come out with good results because the object is relatively small compared to the background. This is from an article that I did for Sky and Telescope. You can just check your back issues. And just how you can target these planetary nebula from the suburbs. But if you really like to image planetary nebula and you have access to a dark sky site, you can expand the size of the planetary nebula and see significantly more detail by going for the outer halos. So what are the outer halos? Well, many planetary nebula, and in this study from I'll show you the reference to a study that was done in the actual astronomy literature. About 60% of planetary nebulas that were studied with, telescopes in the Canary Islands that are a meter or larger, about 60% will have a halo, but it'll be up to 1,000 times dimmer. And these halos are because of the interaction of a faster with a lower stellar wind, and then with photoionization. So this is just from an article that was taken. It was either like one of the astronomy or astrophysics journals, and just looking at what they were doing, and they were doing it from a scientific standpoint. There's not really an aesthetic image, but they would, because they're dealing with a 1 meter or 2 meter telescope, they've got to block the central planetary nebula so they could image the rim, and get these halos. This is just an example of what you can achieve by looking at these halos. What I did here is this is a typical LRGB image of the Dumbbell Nebula, but then I did another layer where here I did 2x2 binning of hydrogen alpha with very, very long exposures, and then overlaid that as a mask, showing that outer halo. Just another example of an outer halo here. Because the native nebula was not red, I suspected hydrogen alpha would not be the best choice for this. I chose a clear luminance for the outer halo, and it was 4 hours unbinned, and it was just put on as another layer, a layer mask. And this is of the Cat's Eye Nebula. Now, the Cat's Eye, without this, it would be relatively small within your image. But by bringing in the halo, then all of a sudden, I think it brings a more dynamic and interesting image. This is the Ring Nebula. And for this halo, I knew from testing it out and experimenting that there was a lot of hydrogen alpha in the halo. So I wanted to get as much detail as much exposure, brightness as I could. So I even went to 3x3 binning and um, in order to get enough data to kind of get over the signal to noise. And this is just 90 minutes of hydrogen alpha exposures. Um, um, and as I'll talk about later, it's often nice to get another object in the image and to balance the image. This is not in the center of the image. It's a little bit off center, but I'll go in a little bit more detail in that later on. So this is from that article from Dr. Karardi, and this is working at the um, telescopes in La Palma and the Canary Islands. And these are just two of their pictures of NGC 6826, a planetary nebula. And just so you know, just to compare to mine, I'll show you in a minute. So you get these stars at these locations. These are background stars through the planetary halo, and these are the same background these are the same background stars through the planetary halo, and um, this is the blinking planetary, which was with a clear luminance bin 2x2. And it only took 25 minutes. It was five-minute exposures of clear luminance. So they don't necessarily take a long time. And as I'm going to talk about here, I try to balance this, kind of use a center of gravity idea is with this star, that kind of a nice kind of orangish star to try to balance and create a little bit more of a dynamic view in the picture. But more on that later. So the next thing is image scale. Now, when we used to, probably 90% of the people in this audience are 60 years or older. That seems to be where most astrophotographers are these days. So we remember that when we used to have our SLR camera, not DSLR, there used to be something called SLR that used something called film, that you know, only have, you know, up to 36 exposures, you know, in the whole um, in the whole roll of film. But anyway, in order to get your pictures proper, you'd have different lenses, and no one would ever go out on a photo shoot with just the normal 50 mm lens. You'd always take a telephoto with you. You'd always take a wide angle, and you really should think about that with optics for telescopes. If you only have one telescope, then of course learn to image with that telescope. But most of us have different telescopes, you know, around, or you can buy camera lenses and get adapters that are very cheap. You can either get a camera lens, you know, get adapter. Doesn't have to be your own brand of lens. If you're doing DSLR, for instance, and you're using a Canon camera, you can buy a Pentax lens and get an adapter for it, because it'll actually fit. There's enough room there. You can do that with you can get adapters for CCD cameras to do camera lenses. And I have a pair of Nikon camera lenses, very high quality. One was actually purchased from a National Geographic photographer years ago, and I got them each for $200 on eBay. Excellent optics, and I got a wide angle refractor and kind of a medium refractor, and Smith Cassegrains that I image at 2000 millimeter for something like a planetary nebula that's very small, or a small galaxy. And these don't have, even if like you have one middle range telescope like a refractor or something, you can buy a Celestar 8, an old Celestron 8 optical tube, used for a couple $100. I was using a Celestar 8 that I used as a child. This is like 20, 30 years old, like 30 years old. I had that I was doing imaging with, and I put it on a better mount, and I'll put my CCD camera on it. So you don't have to spend a fortune. You can spend a fortune, but you don't have to spend a fortune in order to get a wide range of lenses for various focal lengths. So this is an example of why it's important to choose the right scale. This is using the same camera, DSLR Canon 6D. Has a nice large chip, but if I was doing this through my 6-inch refractor at 1160 focal length, I'm not getting the entire view of the North American nebula. But then if I take this to a shorter focal length refractor with half the focal length, same camera, same photographer, same object, you can get a lot more interesting detail because it's will get more context and you can actually see the full length of the object. So let me just I'm gonna go backwards. So this is the same chip, different scope. These are the same scope, different chip. So an alternative, if you have other cameras, you can image objects using a different chip. Using the same telescope. That's a different way to getting scale. Two different ways to accomplish the same task. So here's one way of framing it, and this is a Canon 6D. These are all using my Tech 140 um, refractor at with a reducer to put it at 800 millimeter focal length, and um, the you can see the M101, nicely framed here. Now, why did I frame it here? Well, because I have a NGC 5474 in this corner, and then the other corner you can see NGC 5422. So, and you kind of balance out the other corner with a couple of elliptical galaxies here. So, this is an interesting frame. This might be a little bit better framing here with using a different camera that has a smaller chip, same object, balancing out, we'll kind of get the center of gravity by putting a bright star in a corner. But I think that, this is such a beautiful object. If you get in close, you get so much detail. This is, using a smaller chip on my ST10. And I think probably a lot more time in order to get some hydrogen alpha in order to bring out these star forming regions. But you can get, excellent image quality, sorry, with either a DSLR or with a CCD camera. The one on the left is a DSLR and the one on the right is a CCD. And the difference in quality is not, I think that I got a little bit better, a better view of the outer reaches of this galaxy. But this, I think, was more due to processing differences rather than due to any difference in the quality of one or the other. I think that now DSLRs are so good that you can do extremely well with either one. The big advantage, of course, of CCD, you can do narrowband imaging, which you can't do with DSLRs. You can cool down the camera. So, another big advantage. So there's another example of DSLR versus CCD. And M81, M82, DSLR, and CCD. It's a little bit of difference of processing. I think I was, trying to get the background darker here, and this one I probably should have worked a little bit better to get the background darker. But I did capture a supernova, which is what the arrow is pointing to it. With CCD, you can get the hydrogen alpha region. So I did have a luminance layering with a hydrogen alpha layer, and that helped me get that kind of star. It's not really a starburst, but it's these are hydrogen alpha areas that are along M82. Again, DSLR, CCD, good quality images, both of the Hercules galaxy, both interesting images. Now, why does this look so much better? Well, with CCD, you have greater dynamic range. And I'm able to process it in order to show that dynamic range a little bit better. I'm saturating the center on my DSLR image, but they're both interesting images, so you can do pretty well. And sometimes you do very well with DSLR, and this is, I think equally good, or at least aesthetically pleasing with DSLR of the Pleiades as compared to the DSLR. And this is the image I showed earlier, the using a the DSLR image with a HUTEC modified versus CCD. And I think the differences here are more differences related to processing differences and processing choices, not related to any inherent quality, one favoring the other at this point for a bright object like this. Again, DSLR, CCD, you know, they both have, you can get excellent quality. So don't get caught up in thinking you've got to, if you're doing one or the other, and you enjoy it, stick with it. The differences here are more of scale because the chip on my DSLR is larger than my chip on my CCD. So you have the Cocoon Nebula, this nice dark region. Sometimes a larger field of view, you know, you lose detail in your central object, but you kind of get context. And I think this dark region is as interesting as the nebula itself. All right, and then just one more example that I have of DSLR versus CCD, the bubble and M52 together, a nice pairing. I think that here the larger chip of the DSLR really got a little bit better framing of the object. Here I was coming off the edge of the image. All right, I think this is my last one of the DSLR versus CCD. Again, you pick which one you like. I like them both. Again, I think I have a little bit more sensitivity, particularly I was able to get H alpha, these dimmer areas around the edge. This is more of a color balance difference between the two. Okay, so now that you've chosen what camera to use and you've chosen what telescope to use, what about if you want to image something and it happens to be low in the horizon? Well, when you start looking to objects that are low in the horizon, and I went into more detail talking about this in my article in Sky and Telescope, you have four things that you have to think about. You have to think about atmospheric extinction or seeing, differential refraction, and light pollution gradients. All of these make shooting an object low in the horizon more challenging, but you can still get excellent results if you take a few considerations. So what is atmospheric extinction? Well, if you look at the transmission of light based on its color, as an object approaches the horizon, so this is up at the zenith, assuming an object has 100% light transmission. When you get down to about 45, 50 degrees, you start to look, maybe I'm trying to think of the geometry of it. Maybe it's 30 degrees where you're looking through two atmospheres. I got to do my math. But anyway, you start to have less and less transmission. And red light tends to be the best. So even when you're down only 5 degrees above the horizon, if you have no trees in your way and no light pollution to deal with, you're still getting maybe 25% of your light getting through. That's with red light. But with green light, you're down to maybe around 12% of your light getting through. And blue light, you're having almost no light getting through. And how do we know this? Well, we witness this every evening at sunset, is why the sun turns red, because blue light is being absorbed. Blue light is really not being absorbed, it's being scattered because you're going through I have on the next slide the number of atmospheres. I don't know, it's 15, 20, 25 atmospheres. Anyway, but also it's not only that you're losing light, but your seeing is getting worse. So this is your seeing. So if, like for me, good seeing is 2.5 arc seconds is good seeing for me. And that's at the zenith. If you get to 45 degrees, that may rise to 3.5. If you're down at 30 degrees, it goes up to 4 arc seconds. You go down to 15 degrees, you might be at 6 arc seconds. Down at 5 degrees, you're over 10 arc seconds. So you've got some really blurry images. So this is just another way of separating those two concepts: the effects on seeing and the effect on color transmission. Color transmission becomes dismal for blue as you get lower and lower, and seeing gets worse and worse as you get lower and lower. Other thing that happens is atmospheric refraction. The colors get separated, and they get separated more and more the lower you get towards the horizon. And this is just an example of the dispersion of light caused by atmospheric refraction, and it mostly affects objects below 30 degrees, 30 degrees and low. If you look here at 45 degrees, you have a little bit of dispersion, but not a lot. Your luminance is going to get blurred. So once you get below 30 degrees, you're not, you're going to start to lose a lot of sharpness in your luminance, and it may not be worth shooting at luminance. It may be better to just do RGB if you have a CCD camera where you can selectively filter. If you're doing single shot, you're going to get some smeared colors. If it's low, then if you're really going low down to 15 degrees, then so you don't have to deal with all this blurring and dispersion. Just go with a shorter focal length. So you've got your pixel size gets substantially larger. The other thing that happens as you get lower is you start to look into your neighboring town's light pollution. Light pollution gets worse near the horizon because you're going through more air mass. So even if the light pollution is uniform throughout your whole area, here it is at 30 degrees, your air mass doubles. So your light pollution is going to be double at 30 degrees, even if you're not getting into a worse area. But of course, odds are you've gone to a dark sky site, and everywhere around you is worse than where you are right now. And there it is at the horizon. The air mass reaches 34 to 38 times that at the zenith. So shoot as high as you can to reduce gradients. So how do you plan for this? One of the terms to keep in mind, the top of the movement of an object through the sky is called its culmination. It's at the transit time where it crosses the meridian. So if you are perhaps shooting an object that is reasonably high, do your ladder, do your red at the upslope and the downslope of this curve, because the red light is least affected by these factors that I've been mentioning it. Get your green as you're ascending, blue, and then get your luminance at the very top. If you're shooting a little bit lower, then maybe avoid your luminance. Certainly, if you're shooting 10 to 20 degrees, I would avoid luminance if you have a CCD camera. Or if you have a DSLR, go to a wider focal length if you can. Accept the fact that you're going to get relatively unsharp pictures. So once you've chosen your site, your scope, your camera, and the altitude, other objects to choose. Among similar objects, is it the easiest to image because of declination, size, or brightness? For example, if you're going to look at a globular cluster and you're starting out, which one are you going to choose in Hercules? You're going to choose M13 or M92? Well, M13 is brighter. It's going to be easier to image. Same thing about M22 versus M4. Lower in the sky, down near Sagittarius and Scorpio. It's which are you going to choose? And go for the brighter one. Go for the higher one. as you're getting started. And then can you frame an object with a second object to create a more dynamic image? And that's where planning is. Don't just necessarily center on your object. So there are a variety of ways that you can plan for two objects. If you've chosen your field of view, you can do um, cluster and cluster. You can do nebula and nebula. You can do galaxy and galaxy, and you can mix them up. So this example of cluster and cluster, and this is not just two-star clusters. This is not an accident. This is a third-star cluster. So if I just taken a picture of one of these star clusters, it wouldn't have been so interesting. Well, this one's a little bit more interesting because you've also got NGC 2438, this little planetary, but still, any one of these is not so interesting. But now when you take this and you frame it appropriately, you've got three condensations of light. So that makes it, I think, more interesting. Of course, many of you have done nebula with nebula. The Trifid and the Coon make a beautiful pair to image together. The heart and soul, this is a very large area, and this is I photographed this early on before I was doing DSLR, before DSLRs really were as successful as they are now. So I was using a pretty wide chip ST10, and this was done from my light polluted backyard. And I used the 180 millimeter camera lens in order to get the object. But anyway, either of these are interesting nebula on their own. I think that the two together create a more interesting pair, especially separated by the darkness. The other thing, and I'll talk about this a little bit more, is they aren't situated directly side by side. Just like this, I didn't have them side by side. They're always you try to get an angle, a slope in your image between the objects, and to create a little bit more visual activity. So this is I've shown you nebula plus nebula, cluster plus cluster. This is galaxy with galaxy, M61 and NGC 4301. I think that this is a more interesting composition, bringing this off center of gravity is always put the larger object closer to the center, kind of if you kind of think of it like a seesaw, and you want the center of gravity between the two objects to be kind of balanced, put the other object at the further away. The smaller object is further away from the center. And there's a lot of other background galaxies here, but these are the two dominant ones. Galaxy plus galaxy. And this is a nice mix of a variety of galaxies. Oops, sorry about that. Again, try to make sure that you don't have them all lined up horizontally in a row or vertically. This is you can mix it up, nebula with cluster. This is the bubble nebula in N52. Galaxy with cluster. Again, do it at an angle and kind of aiming for a center of gravity. Here, these are kind of equal weight, so they're kind of equal distance from the center. And this increases the impact of what would be a small object, the Owl Nebula. Hard to get a lot of detail in it, but I think it's interesting when you have it together with M108. And you don't have to balance with another deep sky object. You can balance with a star. So this blue star kind of has a nice kind of balance with the blue oyster nebula. You can use a star with a galaxy. So there's the little pinwheel with a nice red giant star. And it's good to plan this out ahead of time so that you know ahead of time that this is what you're going to be photographing. Again, think about the center of gravity. Think about the seesaw, the fulcrum in the center. You want the heavier object to be closer to the center. It creates more of a visually balanced image. I didn't come up with this concept, but the rule of thirds. This has been around for, over 100 years. And for all I know, the John Thomas Smith that wrote about it may not have been the one to originate the concept, but he's the one who wrote about it. And you can read it there, proportion of 2 and 1 to be the most picturesque medium. And this is not just for dividing the frame, but also for all division of, quote, straight lines and masses and groups. So this is an example of an image and I don't remember which cluster this is. Somebody else in the audience probably could measure. But this is an interesting image, but it just looks static. There's not a lot of dynamism to it. So what I can do is I can crop it. I can apply a frame, and Photoshop has grid lines that are according to the rule of thirds. This is well accepted. So you crop it, you put the object off center. So this is kind of a power position where the intersections of these lines occur. I also prefer it then if I have a second object, do that idea. This is the center of the image. Think of the seesaw, and this is the heavier person and the lighter person, and you're doing this balance. And so you crop it, and then I think this creates a more interesting image. Again, having it going along the angle of those of that rule of 3. So when I was putting together my objects, I didn't want to have, for example, 2 very similar globular clusters, in the same area. I wanted to have a mix. I try to draw from all these other catalogs and try to find things that were interesting. And of course, the book doesn't include the objects that did not make it past the cutting room floor. I was going to have a second book on it, but then if they didn't make the first cut, would you really want to spend your time imaging them? So I ended up not doing it. So the final 100 that made the cut were 21 emission nebula, 6 reflection nebula, 9 open clusters, 7 globular clusters, 11 planetary nebula, 3 Wolf-Rayet stars with associated nebula, 4 supernova remnants, and 39 galaxies, which included 13 groups of galaxies. This is when I was setting this up and how to present the book, I actually showed a few outlines to my wife, and she said, that doesn't make any sense. It's hard to follow, it's just because she's a really excellent cook. And so I said, well, how would you do it? So I do it like the Silver Palette Cookbook, which many of you may remember the Silver Palette Cookbook from 15, 20 years ago. It would always start off with when about something you're going to bake, there'd be a little historical perspective, like say, this apple pie was served in the Lincoln White House, and you have a little historical information about what it is that you're going to be baking or what's the significance of it. And then it would say, okay, what are your ingredients and how do you put them together? That's kind of the imaging part. And then how do you present it, and so forth. And that's the processing. And then they would have a nice picture of the apple pie when it's fully baked, and then, any other footnotes. So that's kind of the way that I presented it. And that was the format that I chose. And I think it was successful. The other thing is I ordered it by date, and I ordered it by the time that it would be in the hit the meridian at 10 p.m. in the 10 p.m. in the summer and 9 p.m. in the winter. Those of us in the Northeast, late at night it gets really cold. So the idea was, when we are going to be wanting to do most of our imaging. So I hope that you've enjoyed this presentation, and my book is still available if you're interested, and I'll be glad to take any questions.
All right. Thank you. Thank you, Ruben. So questions, audience. I saw Brad had a comment. If you've got a microphone, feel free to speak it. Otherwise, I can read it.
Well, it is just a comment, but that when you were saying you don't need more than 100 targets, for the year, maybe, but if you've only got 8 or 10 targets for the month, you might decide you'd want a few more, so it could justify a second book.
Okay, Brad, I'll write another book just for
All
you.
right, thank
I'll
you.
dedicate it to you right on the
That
front
that
cover.
that is courteous.
All right. We got some more comments or questions. I'll start one. An interesting other way, this is really a pitch for next month's talk, to increase your field of view is mosaics now. Maybe those were harder, 15, 20 years ago. But yeah, our next speaker is going to be talking all about mosaics and et cetera, et cetera.
Yeah, I think that's great. Now that there's a lot more automation available, and you can, set up a mosaic before you go to sleep. The disadvantage of a mosaic, of course, besides the added processing time, is it's more imaging time because you're acquiring, let's say you're doing a 2x3 mosaic, you're acquiring 6 sets of images. So
Right.
instead of 2 hours of imaging, you're doing 12 hours of imaging. Um,
Correct.
and that's great. I think you're going to get a lot more detail. Um, the other thing that's changing is that mosaics were you know things things swing, right. The pendulum swings. A mosaic was became important when people were using, like, the ST10 camera was like the hot camera for many years, or the ST2000 was then the economical version of the ST2000. But the ST2000 was only 2 megapixel, and the ST10 was 3.2 megapixel. So if you wanted to have a very high resolution image, enlarging it significantly, um, you couldn't just go to a wider camera lens, or wider field of view, because you'd lose all that resolution. Of course, now you've got 50 megapixel cameras, so you know it's but if you want to image the whole sky, or create this super high resolution mosaic, it's an easier process now than before. Still takes a lot of processing time. And if you have a 100 megapixel image, I mean, or a 200 megapixel mosaic image, you need a lot of computing power in order to process that and to watch it all on one screen.
Another thing I think that's changed, maybe, since, the 2010 era, is the amount of automation there is, so that, like for me, I image out of my backyard, and you have a remote observatory, and it's not that hard to go and collect 20 or 40 hours of a target. If it requires, it may not require it for your remote observatory. It certainly does for my light polluted backyard. Anyway, that's another, you've mentioned a few times about 2 or 6 hours, and in the Bay Area, at least for me, you're talking 20 or 30 hours.
Yeah. Well, my goal with this book is really to get more people involved in astrophotography. And those of us who've been doing imaging for a long time, we have a challenge, and we may be willing to put in 10, 20, 30 hours of image acquisition to really get that amazing shot, that, to get that detail that we're digging for. But you take somebody who's got a DSLR and maybe
Sure.
an entry level equatorial mount. You tell them, okay, you're gonna have to do 30 hours of image acquisition. It's not going to get many people, new people, into the hobby. So
That's for
I'm
sure.
the first to acknowledge that there are a lot of people out there doing a lot more sophisticated and imaging than I ever did when I did this book. But but many of them started out with the 2 to 3 hour imaging, and you're going to get better, right? I mean, how many I mean, how many times have I imaged uh you know the M45, M32, M31, I should say um the Bubble Nebula. I, I've imaged them all, the Cocoon, like 10 times, okay? And each time, well, not each time is not necessarily better. Each time is different. So, um, that's one answer to you, Brad, is that, if there's 8 to 10 objects in the month, well, you know what? If you wait just another 2 hours, you're into the next month.
Mhm.
Uh, 2 hours later in the night is 1 month later in the calendar. Um,
The other
so
thing I'd look for in that second book you're writing for me is, everyone. It's not that any of us have certainly imaged all these objects, but you sort of seek to be different. And so, if you take an object that everyone in the world has imaged, that may be less exciting than, obviously you're not going to find anything no one's seen before, but you're going to find something that you can press. Hey, I've never really tried that object.
yeah, there were maybe 10 to 12 objects that I felt I really wish I'd included uh, in um, uh, in the book. A couple of really nice galaxies that I imaged shortly after I did the book. But as I got into about 50 objects for my second book, um, it got to be harder and harder. They were dimmer objects, they were smaller objects. They started to take, instead of my upper limit of 6 hours that I wanted to have for imaging, they were taking 10, 12, 15 hours to get enough data. And then it was harder to process. So uh, I began to have a little bit less fun with it. Um, but that's me. The other thing is I'm in the Northeast. And I mean, if you just look at my photo here, that's my typical day is, I have a lot more clouds than you do in San Diego. So, um, for me in a given month, I may have 3 or 4 clear nights, and of course, half of them are around the full moon. Um, so,
Well,
you know,
Murphy says they're all going to be around the full moon, right?
Yeah.
Yeah, no.
but you're right, and there are other guides out there that go into some other objects, uh, but it's harder. I do remote when my observatory is an hour and a half away. I will do remote imaging from my cabin that's near the observatory, but I don't do remote imaging from an hour and a half away. I mean, I could, but I'd have to automate my roof on my observatory. Um, and I've had issues with uh, power failures, and and I used to never image the night before I'd have to work. But once it was going to be a really clear night in my observatory, and I figured, well, it's only an hour and a half to get back to work. Let's see, if I get up at 5, I can get to work on time, no problem. So, and I had on my, I had a little trouble getting my telescope going. 11 p.m., I got it, everything started. I went to sleep, everything was automated. And then at 3 o'clock, I got awoken by this loud bleep noise, because that's what happens when my power goes out. And so my power goes out, and I have my observatory exposed to the elements, and I didn't have a backup generator. So how am I going to close up my observatory for the night? So at 3 o'clock in the morning, I'm putting the garbage, bags over my telescopes, and manually slewing them, to horizontal. And I don't have a hand crank for my roof. And um, of course, and then so I lie back in bed, at 4 o'clock, now that that's all secure, and saying, okay, fine, I'll just get up in an hour and a half and get to work. And all of a sudden there's another bleep, power comes back on. So I go back up to the observatory and I close the roof and I seal everything up. And by that time it was time to go to work. So I had 2 hours of sleep, and so So I don't do complete remote. I do remote from the house to the observatory, but not hours away. But it could be done. And I've had a different observatory that was designed that way. I would have done it.
A lot of people also put a webcam on their gear so that even when they're in the house, when it's outside, they can watch it and see if it's doing anything wrong or about to hit something.
Yeah. I mean,
You
well,
you can also get an alternative power source, essentially a battery pack. And those are not too expensive, and they can let you sleep at night. And carry plenty. You can get them different amperage.
yeah. I got one right after that.
Yeah, there you go.
Of course, I've used it
Best sales
0 times in 10 years. But
Of course. No, that's how it works.
yeah, but
Having it stops the power failure.
Yeah, say I have an idea for your second, third, and fourth books. Maybe instead of I can understand how you'd have trouble picking 100 objects, but maybe you could make a little series where you focused on planetary nebulae, which can be pretty bright, and do 50 planetary nebulae, and then 50 of the brightest, sharpless objects with hydrogen alpha, and then 50 of the brightest galaxies, or something like this. In other words, to give focus on something where you go for the brightest of some subsegment of the population of targets, and then just focus on a smaller group. Anyway, that's my
no,
as a
that's
literary
an
agent.
excellent idea, and I like that because then it's 3 books instead of 1.
Right. Well, if you look at, I buy things on Amazon nowadays, to read them with my Kindle. And, you get these things. I read a lot of science fiction, and geez Louise, it's the least publishable unit. The tiniest thing, and they put 5 of them in a series, and they all amount to 1 book, right? So if you're into Amazon publishing of science fiction, there's lots of models out there for putting together, instead of 1 good book, 3 mediocre books, but call it 1 series, Anyway.
Oh, I like that. Very good. Thank you, Jerry. Brad, yep. Brad, you're gonna have to get it piecemeal then. Gonna get it 1 by 1. So, all right.
Well, the advantage of having a series is that compulsive people like to buy a whole series,
I will recommend.
They look good on the shelf. Line up on the shelf.
Right.
I will recommend the later books, even though I still actually do shoot with a CCD. Not too many people are.
Yeah, I do both. It depends on the object.
No, I mean they're shooting with CMOS cameras. They're not shooting with CCD cameras.
I still use CCD cameras.
No, I know they're. I said I still have one. I still have one too.
Yeah, the CMOS are nice. They have advantages and disadvantages, which we're not going to go into here, but mostly advantages. And one of the big advantages is price point. For what you get, for what you want,
and read noise. It's another one.
Yeah.
All right. So do we have other questions for Ruben? I'm going to have to cut this off sometime soon, unless, come on, somebody, anyway.
Hello.
There you
Hi.
Jeffrey.
Hi.
Please.
This is Jeffrey Paulin. Am I allowed to ask Ruben a more beginning question?
You absolutely.
Ruben, I see you're using, it looks like you're using an AP mount. I have a AP 900, and I'm just wanting to figure out one thing that, even though I've got it to work, there must be a way to optimize it. And that is especially with your giant telescope on this system and heavy counterweights. What park position do you start in? And then what park positions do you move it to in order to do your balancing in both directions? Your weight, your counterweights, and then also sliding the telescope back and forth.
Yeah.
What park positions do you use? And do you loosen all 8 of the clutch knobs? And And then how do you reset them so that both axes are correct again?
You know, those are a number of technical questions that I think the astrophysics user group could help you with more than me. I do loosen one axis at a time is the way that I do it. I don't do loosen all the axes. Then you don't know where things are going to be flying all over the place. And I
Right.
don't loosen them completely. I loosen them gently, you know, so that there's still a little stiction to them, so things don't fly out of control. But you're right. You have to do things, and you do think, you know, there's really three different. You know, there's two axis and also the two position, and even that changes a little bit with what camera you put onto it. So you know, but I find that you know the astrophysics telescopes are so robust that you can get by with a lot of imbalance. But there's, you know, other you know, there are a bunch of other considerations, too much to go into here, that I think that the astrophysics user group, you can, let's see, how did I join that user
I'm
group?
in it.
You're in it, okay. You know, the moderators who are, you know, both geeks and a lot of them are on the staff of astrophysics can help you with that. And I'm going to defer to them. But you know, I've just a couple of things. In order to tweak my weights and in order to sometimes adjust for adding a piggyback scope and taking off a piggyback scope, rather than going through all this process all over again, you know, I get it balanced. And then if I'm adding on a wide field, you know, by wide field, I mean a 200 mm lens, let's say, piggybacked for something, I'll just take like an ankle weight, you know, it's, you know, a little 3 pound ankle weight or a 5 pound ankle weight, and just throw it at the end of my counterweights to approximate what I think, you know, to compensate for it. I don't think you have to be that precise. I think that for the bulk of your image, you want to be as precise as possible, but you don't have to be uh, uh, completely balanced. You know, the scope will compensate for itself. You know, I recently, you know, for the eclipse, I took off one of my refractors, one of my 3 refractors, and I didn't rebalance it. And I have no problems with my mount. I'm probably stressing it, and it's probably not healthy for it. But there's a lot of forgiveness on a robust mount like the astrophysics. Anyway, guys, I'm going to sleep because it's 3 hours later for me here.
Sorry about that.
For
Okay.
work. But it's really been a pleasure having you guys. And thanks.
I
Thanks
hope
for
you didn't
inviting
miss a clear night.
All right. So why doesn't everybody unmute themselves and give Ruben a big hand? Thank you so much, Ruben, for that presentation. Thank you.
Thanks, Ruben. That was an
Thank you
excellent presentation.
Thanks so much.
Thank you.
I think I'll buy your book.
Oh, well, thank you.
I got it, so.